Okay, so first I would like to introduce Eric. So he is a two-time International Mathematical Olympiad gold medalist. He is also currently studying at Harvard University. He is currently studying mathematics. And when Eric is presenting, please mute yourself. And if you have any questions, please type them in the chat. So Eric, time is yours.
Yeah, sure. Thanks, Stephen. By the way, you can if there are any questions, please just let me know. You guys are totally free to ask any questions throughout. And I imagine you might as time goes on. So let me just share my screen. Okay, this works, right? Do you guys see this? Is it see? It's moving, right? Okay, I hope it works. Wait, do you guys see my screen? Just making sure. Yes. Wait, Steven, do you see my screen?
Yeah, I see your screen. It's
okay. Good. It's this one, right? Not the other one.
Yeah.
Okay, cool. Sorry about that. Great. Okay, cool. So as Steven said, yeah, I'm a sophomore at Harvard studying math and physics. And yeah, today I'll just be giving this talk on a problem that I think is a very good way of, well, one of my favorite problems to introduce this really cool topic in higher math / uni math called algebraic integers and algebraic numbers. So the problem goes like this. The problem is this. We have n lengths arranged evenly spaced in a circle where n is greater than 2. Okay. So for example, when n equals 8, we can have this little octagon here. Initially, one of them is turned on and the rest are off. So here, blue means on and red means off. What we can do at any point in time is choose any regular polygon whose vertices are lynched and toggle all of their states simultaneously. So for example, we can choose this square here, which is like a diamond so-called, and toggle all their states, as in turn the ones on to off and off to on. So here, in this diamond, we turn the top one from on to off, and then the other three, the left one, right one, and bottom one, from off to on. And so we end up with going from this state on the left to the state on the right. And we want to find for what positive integers n is it possible to turn all the lengths off after a finite number of summing operations. Okay, so that's the question. Now, how do we tackle these kinds of questions? These kind of in general, when we have a very broad question where we're allowed to do a lot of things, but it's not really clear how we can analyze all of the little things we can do. Something that's usually good to think of is an invariant. So instead of telling you what an invariant is explicitly, I'm just going to give you a problem that I think is a good example of, what an invariant is. So this is a problem that maybe your grandpa or grandma or your math teacher has shown you, but I think is a very good example, which is, let's say we're given an 8x8 chessboard, right? And we're given we have the two opposite corners of this chessboard are taken. Can we still cover this chessboard with stones? I'll let you guys think about this for a little bit. Okay. So I guess it's kind of hard to think about, unless you have pen and paper with you. But the answer turns out to be no. Why? Well, what we can do is we can color the chessboard, with our usual chessboard coloring, black and white. And it turns out, well, first of all, if we take out two opposite corners, well, these opposite corners always have the same color. So, originally in our 8x8 chessboard, we started with the same number of black and white colors, squares. But now we have more white than black in this specific chessboard. And what we also know about dominoes, and this is very important, is that dominoes always take up exactly one white and one black square. So no matter how we tile our things with dominoes, we're always taking up the same number of white and black. So if our final state doesn't have the same number of white and black squares, which is the case here, then we're done for. We can't do it. And that's the reason why we can't color this 8x8 chessboard with dominoes. So, this is a very standard problem, but really the essence of this problem is this, right? We consider this chessboard coloring, And in this chessboard coloring, we have that these, like, why we consider this is because these dominoes are like, work very well with the chessboard coloring, right? They like always satisfy some property that never changes no matter what. Hence, an invariant. In this case, the invariant is the fact that, like the number of white and black squares taken up is always the same. And so for this problem, since we're also working with a similar problem where we have a huge structure of like a lot of different moves that we can do, what we'll want to do is find a similar invariant for this ring of lights. So how do we construct an invariant for this ring of lights problem now? What I'm going to tell you now is a very nice way to do this is through something called the roots of unity. Now, just as a raise of hands, like how many of you guys know about like complex numbers and are relatively familiar with them so far? Just like feel free to just like, I guess I can look at the participants list. Well, I'm not sure how to do this. Yeah, like feel free to like raise your hand, Zoom chat or whatever, or the participants thing. Okay, I'm not gonna wait too long, but it seems like some of you know about complex numbers, but not all of you do. So what we can do, so I'm gonna talk a little bit about that to you guys for now, as a little bit of background. So first of all, so the roots of unity are a type of complex numbers, so let's talk about complex numbers. The idea behind complex numbers is this. If we have that pi is, if we consider like, like usually when we have like positive numbers, when we have real numbers, what's special about the real numbers is that a negative number times a negative number is always equal to a positive number, or like a non-negative number. And in particular, we always have that two, like any two number multiplied by itself is a positive number. So a natural question to ask is, like what kind of number multiplied by itself is equal to -1? And clearly this number cannot be real. So in this sense, we define I as a number satisfying that I squared is equal to -1. And the complex numbers are the numbers that are made by, like the real numbers of A plus, like the reals times this imaginary quote unquote number I. So in my opinion, the best way to think about complex numbers and the way that we will think about them today is by graphing them on the complex plane. So basically what I really mean here is, since we can write every single complex number as like A plus BI, we can think of them, like instead of just like a usual number line, we can have like a number, like plane, where we have both a real line, real axis, which is like a usual number line, plus an imaginary axis. And with this, we can, like describe them using, describe each number based on both their real, each complex number based on both their real and imaginary components. Now, why this graph interpretation is very useful is because a great way to think about complex numbers is in terms of their distance from is not in terms of their components onto the real and imaginary axes, but in terms of their distance from the origin, also known as their magnitude, along with the angle they make from the real axis, which is their argument. This is like the angle that's like that they make when they like you turn them clockwise away from the positive real axis, or counterclockwise away from the positive real axis. So why this interpretation is especially useful is because of the following very famous result, known as the Moivre's theorem. So how this theorem works is like this. So if we're given any two complex numbers, the magnitude of their product, Z1, Z2, is equal to the product of their magnitudes, of the magnitudes of Z1 and Z2. And the argument, so the angle of Z1 times Z2 is the sum of the arguments of Z1 and Z2. Oh, something I may have forgotten to mention is, like, you can multiply, complex numbers if like you are familiar with this by like just like multiply like A plus BI times C plus DI. You can like, I guess I'll just like write on this a little bit. It kind of works like this. For those of you that aren't super familiar with this, you can just like multiply it using like FOIL, where you can like multiply this and this, and then this and this, and then this and this, and then this and this. Something like that. Yes, okay, great. And then this gives you, like, for example, this gives you, and you use the fact that I squared is equal to -1 to get that this is equal to something like this. BC plus ADI. Okay. Anyways, we can move on for this. And basically, like this multiplication, as it turns out, both multiplies the magnitudes and adds the angles. And this second part is very important because, like, you can like it doesn't seem like too unrealistic that like like the magnitude would be multiplied, right? But like the angles being added is something that's very unique to complex numbers and very, very powerful. And this is something that will really be useful. In particular, this makes it very geometrically intuitive to multiply complex numbers, especially when the complex numbers that we work with all have magnitude 1. Because in this case, like since their magnitude, the magnitudes of their products will also almost have magnitude 1, multiplying a complex number is basically just like like adding its angles, right? And so that's like really the only thing we have to keep track. So just as like a little geometric interpretation, this is kind of how you would usually multiply complex numbers. Well, we're given Z1 and Z2 here. Oh, I'm not sure if I'm annotating. Okay, great. So we have Z1 and Z2 here. Their magnitudes are R1 and R2 respectively, and their angles are theta 1 and theta 2. And well, how do we multiply these complex numbers? Well, their magnitude are multiplied. So now we have something of length R1 and R2. And this angle over here, this bigger angle, is equal to the sum of this angle and this one. So the sum of this angle and the sum of this angle. Does that make sense? Okay, hopefully it makes sense to you. Okay. So that's kind of like just like how multiplying complex numbers work. If for those of you that are relatively unfamiliar with this. Now, why? Well, like why are we like so? Just to like bring us back a little bit, we were originally discussing, like this invariant to this problem that we want to solve, and suddenly we got like warped into this like little rabbit hole of like complex numbers. And why do we care about these complex numbers? Well, there's a very specific set of complex numbers that are very, very useful and will turn out to be very, very useful for this problem, which are known as the roots of unity. So what precisely are the roots of unity? They're the solutions to the equation x to the n equals 1 in complex numbers. And they turn out to be a very good way of keeping track of like regular polygons from an algebraic point of view. So before we get into any specifics, let's consider this equation, right? This is a polynomial equation x to the n equals 1. And let's think about like what kinds of complex numbers would satisfy this. So if we have a complex number x which satisfies the x to the n equals 1, well, we can consider its magnitude in its argument. Well, we know that its magnitude, well, it has to be a real positive, like non-negative real number. And if a non-negative real number to the n is equal to 1, then okay, that real number has to be 1. So we know its magnitude is 1. Great. What about its angle? We know that multiplying two complex numbers adds their angles. And since exponentation is just repeated multiplication, we have that, x to the argument of x to the n is equal to n times the argument of x, because like exponentation, as we just said, is repeated multiplication, and so n multiplication is repeated addition. So what this means is, well, we want their angle. So we want this angle here. We want to be able to add it n times. For example, here's the case of n equals 5. So this is like 2 theta, 3 theta, 4 theta, and then we're back at the real axis, and this is equal to 1 again. So basically, we want n theta to be equal to a multiple of 2 pi, because if we, like any angle that's equal to 2 pi is basically equal to 0, because like 2 pi just brings you all around the circle. So what does this mean about our x? Well, as we stated before, it has a magnitude of 1, and its angle is an integer multiple of 2 pi divided by n. So what this looks like on the complex plane is this, where this is the case of n equals 6. So this looks like, well, this looks like a regular hexagon, and this is pretty magical. The fact that somehow through this, like seemingly unrelated algebraic equation, we've suddenly gotten a regular polygon that we can, a good algebraic way of representing a regular polygon. And of course, the reason why this is true is because 2 pi over 6 is just moving. Basically, our first solution here that's not equal to 1 is like basically 1 rotated by 2 pi over 6, and the next solution is rotated by another 2 pi over 6. So that's how you kind of get all of these solutions being like a regular hexagon and so on. And of course, there's a case where n equals 6, where n equals any number, then it's going to be a regular n-gon with one of its vertices on equal to 1, and its other vertices also on the unit circle. Great. Just some formalizers. One property that we will be needing about the roots of unity is that for any root of unity, omega is satisfying omega to the n equals 1, but omega is not equal to 1. We have that 1 plus omega squared all the way to omega to the n plus 1, n minus 1 is equal to 0. It's a very complicated equation, but basically what it means here is, well, okay, 1 is this thing, omega is this thing, omega squared is this thing, omega cubed is this thing, omega to the 4th is this thing, and omega to the 5 is this thing. And we want to show that, like their sum is equal to 0. There's a nice algebraic way to show this that I'll show soon. But intuitively, why this is true if you know anything about complex addition is because basically when you add two complex numbers, you're basically just like playing them head to tail.
我觉得这个不用热。
Sorry. Okay. In any case, so like given two complex numbers z and z prime, their sum is like this. It's what you get when you put z prime at the like the end of the beginning of z prime at the end of z prime. So that's z prime. So why this makes intuitive sense now is because when you add up all of these 6 complex numbers, well, like you're going to get like something that's like close to like their like average or whatever. Like the direction is close to their average, but since like they all point in like a symmetrical direction, their vector sum basically cancels out, so to speak. It's okay if you don't really understand this, but this is kind of just like a formalism, I guess, that will like need as like part of the algebra. And just as an algebraic point of view, why we know like how we can prove this is true from a mathematical like algebraic point of view? Well, this is like like a geometric series. You can write out the geometric series, and then you realize the top is 0 while the bottom isn't, so the entire thing is equal to 0. Okay, so now why did we talk about all these complex numbers? Okay, let's return to our original question. What was our original question again? It was about the ring of lights, right? N lights in a circle, like a regular polygon, where one of them is lit up and the other one is not. All the other ones are not. So we want to consider an nth root of unity, omega, such that we're going to have it be like sort of primitive. This is not super important, but basically we're just going to be considering the root of unity that is like has magnitude 1 and is like 2 pi over n away from the origin, rotated away from the origin. So it kind of looks like this, I guess. Like here, and then you rotate it a little bit. It's more like pi n equals 5. I like 2 pi over 5. So it's like kind of like the first vertex in the regular polygon. Sorry, this is a terrible diagram, but hopefully you get the point. Okay. So we had that. Well, like if we're given like an nth root of unity like that, well, as we described before, we know that we can like sorry, give me okay. We know that it's so if we have something like this, I'll do n equals 8 to be consistent with the diagram. Then we know that if this is 1, this is omega, then omega squared will be like here. This will be omega squared in the column of length, omega cubed, and then so on. Kind of go like that. Right? So in some sense, it would kind of make sense to, attach, sorry, there should be powers, not subscripts. It would be kind of make sense to attach these powers of omega to these rings of light, these lights. So how we can do that is shown in this little diagram here, where we're going to attach 1 to the first light, the 0th light is here. So like to like omega to like this light that's lit up. And for every other light going counterclockwise, we're going to attach the next power of omega. So omega to the 0, omega to the 1, omega squared, and so on. Okay. So what does this do for us? Well, we can also do, well, like that's fair and all. We've attached these kinds of like weights to these lights. And that's like cool, but that doesn't really do anything for us yet. And remember, our problem was really about toggling. Like we toggle it on or off, That's really what like we want to analyze. So let's also add a label for that. where we're going to attach to each light the number of times it's been toggled. So for the light that's already like weighted among to the 0, we're going to give it a coefficient A0, which is going to be the number of times it's toggled. Of course, when we begin, what we're going to say is that the blue light has been toggled once and every other light has been toggled 0 times. So as you can see in the diagram, A1, A2, A3, A4, and so on are all equal to 0. Okay, big setup. What is this all for? Well, let's think about let's go back to, the question itself. The main point of the question was that we had this little operation where we could toggle all the lights that are in a regular polygon. Well, what does that precisely look like? Let's say we toggle like the ones over here. Basically, what we're doing is, let's consider the weights, right? The omegas. We have that every single time we talk, like this one corresponds to some weight, omega, and this one is like, okay, omega times omega squared. And since it's a regular polygon, this one's going to have the weight omega times omega squared again, which is equal to omega to the 5th. This one was equal to omega to the 3rd. And this one, you add another omega squared. So these weights, the powers of omega that go into these weights form like an arithmetic sequence, right? Okay. So now, so what our operation actually does here, I used a slightly different, toggling thing, but it's the same idea, is that we toggle like these weights and we add 1 to each of, the AIs the AJs that lie on them, because those are the toggle counters, right? So now, what is something that we can say about these toggle counters? Well, we know that, when we consider these weights, since they lie on like a complex, since they're all like a regular polygon, these weights, these omega powers, all sum to 0. In particular, what we did is we increased each of the AJs, so the toggle counters that corresponded to these weights, by 1. So if we consider this sum, let's consider the sum here. So it's going to be, give me a second. Let's consider the sum of A0 omega to the 0 plus A1 omega to the 1 plus and so on to A7 omega to the 7. Okay. Great. So we have this counter here. So what have we done to this counter? Well, every single time we toggle a regular polygon, we add, like 1 to some of these, like some arithmetic, sequence worth of indices worth of like these like AJs. And so what that does to the sum is it adds this like weighted sum is it adds like omega to the x plus omega to the x plus e and omega to the x plus 2e and so on. So it really adds these weights every single time. But we know that these weights for any regular polygon sum to 0 by our like symmetry argument from before. So in fact, what we have is that if we consider this weighted sum here, this weighted sum of A0 omega to the 0 plus A1 omega to the 1 and so on. This weighted sum, since we're adding it, we add 0 to it every single time we toggle, like n vertices, a regular polygon of vertices. This weighted sum never changes because of these like this inherent symmetry we have from these roots of unity. And this is really powerful because what this means is that now, finally, after all of this like complex number stuff, we have an invariant. In particular, we know that, well, when we started off, this sum of the AJ omega to the J's was just equal to 1, right? Because all the AJs were equal to 0 except for this one over here, this one. And that gave us, and for this one, AJ times omega to the J is equal to 1. So this invariant here is always equal to 1. And so this is finally something we can analyze about this process. Got it? Okay. By the way, again, if you have any questions, feel free to just like put it in the chat. And like Steven, you can like let me know if there are any questions already. Great. So now, what do we do with this invariant, right? Well, we're not just done when we have an invariant, but rather we're done when we realize, but we need to like use the invariant to solve the problem. So basically, let's now return to our original question, right? What did we want to be true? Also, maybe, what is omega? Oh, okay, sorry about that. Omega, as we described before, basically we chose omega to be like an nth root of unity, right? Basically, basically we wanted it to be the specific nth root of unity that was like 2 pi over n rotated away from 1 in the complex plane. So if you know this notation, we just chose it to be this. Yes. And why we chose it is because then we can weight all the like vertices of the ring of lights with powers of omega, because it's an nth root of unity. Does that make, yeah, hopefully that makes sense. Okay, so that was what we chose at omega to be. Great. So our original question was this, right? We had this one operation, and we wanted to see if it was possible for all the lights to be off at some point. So what does that correspond to? Well, like this total number just keeps on going up and up and up. But we know that a lamp is off if and only if its toggle number is even, right? Because then it's been on, off, on, off. You want it to be like an even number of times, so it's off again. So we want to see if it's possible for us to eventually have that all of the AJs are even. What we know from our invariant is that the sum of the AJ times omega to the j's is equal to 1. So we want to see if there's a solution to this equation here where the invariant is equal to 1 and the AJs are all even integers. If there is a solution, we're not yet done, because we still have to see if we there's some way that we can get to this state by only this state of the AJs using only our polygon processes. But if there is no solution here, then this invariant already tells us that it's impossible for us to use these polygon transformation, polygon operations to get to the final state that we want, and the problem is already solved. So basically, we've somewhat reduced this problem to this final equation here. To now solve this equation, we'll need to use something called algebraic integers. So this is pretty cool stuff. But before we get to algebraic integers, let me talk about something called algebraic numbers, which are kind of like a generalized form of algebraic integers. So how algebraic numbers work is like this. Let's remember that, so just as a refresher for those of you that don't quite remember this, a polynomial is something that's of the form, is like an expression of the form Cn times x to the n, plus Cn minus 1 times x to the n minus 1, plus all the way to C of 0 x to the 0. Where the Cj's here are the coefficients. Okay, when the Cj's are all integers, we're going to call the roots of this polynomial algebraic numbers. And for reference, we'll call, when the Cj's are all integers, we'll just call this polynomial an integer polynomial. So more strictly, we define an algebraic number to be any complex number that is the root of an integer polynomial. Okay. This is a pretty complicated definition, especially if you're not super familiar with polynomials. So it's kind of like, give us a little refresher on what is and is not an algebraic number. Okay, so let's think about this, right? Well, is 1 an algebraic number? Well, it's the root of, it's x minus 1, right? 1 minus 1 equals 0. So, and x minus 1 is an integer polynomial. So, great, it's an algebraic integer, number. What about, n? For n and integer. Well, we have the x minus n. Oh, that's almost a. Oh, please wait. Please do not write on the board. Sorry, you can write that later, but not while I'm talking. Thank you. Okay, Stephen, switch perms or something, or I don't know. Anyways, back to the top. So so any integer is also an algebraic number. What about a rational? Let's say we take, 3 over 2, right? Well, x minus 3 over 2, that's not quite an integer polynomial. That's like a rational polynomial, because 3 over 2 is not an integer. What about 2x minus 3? Well, 2 times 3 over 2 is equal to 3, so that minus 3 is equal to 0. Great, so it's an algebraic number. So in fact, every single algebraic number, every single rational number is an algebraic number. And this in the similar way. Okay, if it's only rational, that's kind of boring, right? What about, let's say, root 2? Can anyone think of, a polynomial, an integer polynomial that root 2 is a root of? Just say it in the chat or something. X squared minus 2. Fantastic. Sorry, I don't know who said that, but Very good. Exactly. X squared minus 2. Oh, actually, I'll just check. Okay, my screen is too small. But thank you to whoever said that. Why this is a root of x squared minus 2 is because, well, root 2 squared is equal to 2. So that minus 2 equals 0. Great. That's an integer polynomial. X squared minus 2 is an integer polynomial, so that's an algebraic number. In particular, in a similar vein, the square root of any rational is also algebraic. You could just do like a similar thing. Okay. Is there more? Well, what about I? Well, we define it as just root -1. But -1 is also an integer. So in fact, I is also algebraic because we never gave any restrictions on whether these algebraic numbers, couldn't be like imaginary or not. And in fact, we said that they were just like complex numbers in general, not just real numbers. Great. In fact, anything that can be written with only radicals of plus, minus, times, divide is algebraic, so long as it's not like infinity or something undefined. For example, this humongous complicated expression is algebraic for the reason that, this is because of something called like the algebraic numbers being a field, but this is not like super important for you guys to know right now. But this is a pretty cool fact. This somehow is the root of some integer polynomial. However, not every number is algebraic. In fact, the vast majority of numbers aren't in some set theory like sense. I'm not going to get into like most of these examples, but it turns out that pi and e are both not algebraic integers somehow, but numbers somehow. All of this is like very, very, very hard to prove. Okay. Apparently I can't share. Okay. Apparently I just trying to not run the board, by the way. Until after the presentation is done, I suppose. And thanks everyone for your cooperation. Okay, great. So that's the algebraic numbers. This is a pretty cool concept, and this is already something that people, often spend their lives exploring. But that's not what we're here about today. Today we're about algebraic integers, not numbers. So what's the difference? Well, let me lead you through this little thought experiment, right? So every integer, we were thinking before, every integer is the root of an equation x plus c0, where c0 is an integer, right? If we have 5, well, that's the root of x minus 5, right? But and evidently, a rational number that isn't an integer cannot be written this way as a root of such an equation, because the roots of these equations have to be integers. But, this begs the question, right? Can a rational number be the root of some integer polynomial with first coefficient equal to 1? So, can it be the root of some x squared plus ax plus b, or some x cubed plus ax squared plus bx plus c, or something like that? And it turns out, by something known as the rational root theorem, that the answer is no. So if a rational number r is the root of some polynomial x to the n plus some integer polynomial with its leading coefficient equal to 1, so this coefficient of x to the n, then we have that r is in fact an integer. You won't really need to know the proof today, but I'll just cover it for those of you who are curious. Basically, you write r in its lowest terms as p over q, and you plug it into this polynomial, since you know that when you plug it in, it's equal to 0. So you get this equation once you multiply by q to the n at the bottom. Okay, but let's think about this equation, right? We know that p and q, they have GCD 1. So q doesn't divide any power of p, because they share no prime divisors. But q divides everything here. And it also divides this 0, because everything divides 0. But it doesn't divide p to the n. So this is a contradiction. And so this is actually impossible. We cannot have the fact that q is not equal to 1. So q has to be equal to 1 and r has to be an integer. Okay, sorry. Great. So with this in mind, okay, now this is somehow, by having this leading coefficient, necessitated to be equal to 1, we have found we've suddenly restricted our set of algebraic numbers by a little bit. And this is exactly how we're going to define the algebraic integers. Since this is somehow a way to differentiate between real rational and integers. So an algebraic integer is defined as a number that is a root of some integer polynomial with leading coefficient equal to 1. Let's now think about, what is an algebraic integer? And what are some examples of algebraic integers? As we already talked about, integers, every single integer is an algebraic integer. But rationals, any other rational is not an algebraic integer. Okay. What are the next most complicated thing, the next complicated thing we talked about. Well, we talked about root 2. Is root 2 an algebraic integer? You guys can decide, like, think about this for a little bit, and feel free to like comment. So is it the root of some polynomial, is some integer polynomial with leading coefficients not equal to 1? Okay, the answer turns out to be yes. Well, if we think about it, like we knew that root 2 already wasn't a root of x squared minus 2, right? This is how we knew it was an algebraic number. But wait, the leading coefficient here, x squared, this is the biggest coefficient, right? The coefficient of x squared. This is just equal to 1. We just have an x to the n. We don't have x to the n multiplied by like 3 or something. So yes, root 2 is in fact an algebraic integer. Great. But what about, like other radicals? We can do something similar for like root 3, root 5, root 6, and so on. But if n is irrational, it turns out that root n, and if n is irrational that is not an integer, then it turns out that root n is in fact not an algebraic integer as well. This is something that's like, you can prove it with a little bit of work. But the easiest way to like figure this out is because it turns out that the product of any two algebraic integers is also an algebraic integer. And using this, you can like realize that this is not, but since rationals are not algebraic integers, neither are the square roots. Okay. What about I? Well, I was the root of x squared plus 1, right? Okay, that leading coefficient, well, is equal to 1. So I is an algebraic integer. In fact, any a plus bi, where a and b are integers, this also turns out to be an algebraic integer, but you might need to do a little bit more work to show this. And in fact, now, one of the most important things about algebraic integers, well, not really most important things, but one of the most important things we'll need to know about them today is that all roots of unity are algebraic integers. And why that's the case is because, well, we define them as the roots of the polynomials x to the n minus 1. And leading coefficient there, that's equal to 1. So fantastic, they're also algebraic integers. Okay, now, we'll also need two more important properties of algebraic integers, one of which is pretty simple, one of which is also simple but much more complicated to prove. The first one is that if a is an algebraic integer, then so is any integer multiple of a. Okay, let's think about why this is true, right? I'm going to give you a pretty easy example. So let's just work through it for root 2. We know that it's a solution to x squared minus 2. So it's an algebraic integer. What about 3 root 2? Well, we have that it's a solution, so we know that, like x divided by 3, that's equal to root 2. So that squared, oh, please not write that part by the way. That squared is equal to root 2. So this minus 2 is equal to 0, so it's a root of this equation, right? But this is not yet, if we like expand this out, this is x squared over 9 minus 2. This is not what we want, because we want integer coefficients. So the way to make this into an integer polynomial, well, we can just multiply by 9. So this is equal to x squared minus 18. And it's still a root here at them. And in fact, we can do this in any polynomial, and this for any like algebraic integer in the sense that, like if we write this out, we can just multiply out by the denominator if it's like, like ma. But we can multiply by x to the n, and a polynomial, and get an integer polynomial, which ma is a root of. And so this gives us the fact that, like, oh, if a is an algebraic integer, then so is any integer multiple. And this is kind of like flying over your head a little bit, don't worry. This is just like a little formal stuff for those of you who are a little more experienced. But please do not write on that one. Right. Fantastic. The other property that we will be needing today is the fact that if x and y are both algebraic integers, then so is x plus y. The reason this is true is pretty complicated, and I won't get into it today. There's a lot of field theory and like stuff that's like pretty like high up. That's an interesting fact. And we'll just take it for fact today, but if you want to read more, I'll be giving a lot of resources at the end. Okay, great. So now, finally, we can return to our original question. So what was our original question again? Well, like after all of this invariant stuff, we reduced it to this problem of, is it possible for a0 times omega to the 0 plus all the way to a(n-1) times omega to the n-1, where omega is is equal to e to the 2 pi I over n, so like a primitive n-period unity. Is this sum possibly equal to 1 where the h's are all even? Okay, well, the h's are even, right? We don't really that already gives us some like excess information. So let's use that. We know that aj is always equal to 2bj for some integer bj. So let's divide out the two here. Then this equation becomes, is it possible for the sum of bj omega to the j to be equal to 1 over 2? Okay, let's think about this equation. So what do we know about all the omegas? Well, we know that every single root of unity is an algebraic integer. So all of these, omega to the 0 all the way to omega to the n-1, these are all algebraic integers. What about the bi's? Well, we know that the bj's are all integers, and we know that integer multiples of algebraic integers are all algebraic integers as well. So this is an algebraic integer. This is an algebraic integer, and everything in between. Finally, we know that the sum of any two algebraic integers is an algebraic integer. So what does that mean? That means that, if we do that a bunch of times, this entire sum is an algebraic integer, right? Okay. But wait, can 1 over 2 be an algebraic integer? We know that the rationals, if they're an the rationals that are not algebraic, that are not integers, are not algebraic integers either. So this is not an algebraic integer. Uh-oh. Well, our left-hand side is equal to an algebraic integer, and the right-hand side is not. So in fact, this solution has no solutions, no matter what our n is. And that solves the problem. So to put it more concisely, by our previously established properties, we know that the sum on the left-hand side is an algebraic integer, but the right-hand side is not, because it's irrational. Please do not write in the board. Because it's irrational, that is not an integer. So this gives us a contradiction, and so for no n is it possible for our ring of lengths to be for us to be able to toggle our ring of lengths to get what we want. And so the answer to our original question from the very start is for no n. Okay, hopefully you guys thought this was pretty cool. So now I'm just going to give you a little bit of background on okay, when is this stuff used? So algebraic integers, okay, from this problem, this is a pretty cool problem in the sense that you have this problem that's combinatorial, right? This is a counting problem where you want to prove some property. And somehow through this entire complex numbers, invariant algebraic number rabbit hole, we got into this number theoretic problem, a number theory problem that somehow is solved by this cool concept of algebraic integers. So, and in particular, algebraic integers, are even though this problem is cool, it's not something that's super important. And algebraic integers are something that's used have much more uses beyond just these little problems like these. So just a little bit of background on them. Integers and rationals are the basis of number theory, right? That's kind of what the entire theory is about figuring out what we can do with certain classes of numbers. And if there's especially in the field of time-fancy equations, where we want to see if certain equations have integer solutions. What's the most famous example? That would probably be Fermat's last theorem, where we want to see if x to the p plus y to the p is equal to z to the p has a solution in x, y, and z, not all equal to 0, for a prime p that's greater than 2. And in particular, why algebraic integers are important is because they're a very good generalization of this concept of integers, in the sense that integers have this divisibility thing, and this this good structure of plus times minus divide and exponents that not every real number works well with. especially this divisibility and like prime factorization part. These two are very important. And algebraic integers, like in some sense that I won't get into today, but you can learn about, also has an analog of this with like for those of you that want to learn about this, ideals and ideal factorization. But also like they also make like factoring an equation much more flexible in the sense that instead of just working with just like integers, you can now factor equations like x squared minus 2, which you couldn't originally factor with only integers. So in particular, algebraic integers were like very heavily involved with and like their theory of like their factorization and whatnot were very involved in like some of the very first proofs of the Fermat's last theorem in the case of like small p, among other many important results. And they were like some of the ways in which we got like 40 values of like primes for which Fermat's last theorem was true, which was a huge breakthrough, like back in the 1800s and whatnot. So if you want to learn, so algebraic integers are something that's like basically like a foundation of modern number theory. And if you want to learn about them, here are some like resources. Of course, algebraic integers and algebraic numbers in general are pretty like like advanced fields. And if you want to learn about them, I first recommend learning some linear algebra, which you can learn through something like Shellman-Axler's linear algebra done right. But there's like millions of like linear algebra textbooks out there, so you are not like without any resources on this front. After this, also before you do this, you should be very familiar with like high school mathematics, like solving systems of equations, which is basically what linear algebra is all about on like a very basic level. Also stuff like complex numbers, which as you can tell today, tell from the talk today, were very, very useful and very, very fundamental. Also, to get more into this algebraic integers kind of stuff, more like what I taught you today most of it can be found in chapter 15 of a legendary book called Michael Arden's Algebra. But if you want to get this book is you have to read like the previous 14 chapters to get to this 15th chapter, except for like maybe chapter 13. But this is a book that really is a fantastic resource if you want to get to on that road and learn about these things called groups, rings, and fields that are absolutely the basis of modern mathematics, and are also kind of the basis of this theory of algebraic integers, which is so interesting. And if you're already through that entire rabbit hole, you can look into this book called Daniel A. Marcus's Number Fields. But this is for those of you that are very, very advanced. So yeah, that's about it for today. Thank you all for all of your cooperation. And now feel free to ask any questions. I'll be here for a while. And thanks for Stephen for organizing this and whatnot. Great. So yeah.
All right, great. Thank you, Eric, for your fantastic presentation on algebraic integers. So does anyone have any questions about his presentation?